Good morning to all. So this is our 32nd lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture we have started our discussion on the unsteady wave motions, and specifically we discussed about the moving shock waves. While we discussed the moving shock waves, we have studied how density ratio, temperature ratio and mass motion are actually imparted to the fluid medium, and then we found that if a shock wave of infinite strength passes through a fluid medium, then it will be getting a Mach number Vp by A2 Mach number of 1.89. So that is something which we have actually done in the previous lecture. One important point I would like to highlight from the previous lecture is that uh, we have considered a situation that here we are having stagnant fluid where V1 is equal to 0. Say this is given by state 1, and say this is my moving shock wave which is moving with velocity w, and in the portion through which it has already passed through, there it has imparted mass motion, and let's consider the state at this point is designated as 2 and velocity of this mass motion is Vp. Okay. So one important point is that if you see the enthalpy of this particular region which is having stagnant fluid, that will be equal to H1, and as its velocity is 0, so this H1 will be equal to its H01 stagnation enthalpy also. Okay. On contrary, here if you see, here enthalpy is say H2, and then we will be having some mass motion also, so total enthalpy will become Hp plus Vp square by 2. Okay, so that will be becoming our total energy. So this will be equal to nothing but our H02. Now one important point is that whenever a shock wave passes through a fluid medium, what it does, it increases its properties. Okay, so it means that H2 has to be greater than H1, because H1 was corresponding to the stagnant fluid medium. When shock wave has passed through it, it has actually increased its pressure, temperature and all the static properties. So that's why we will be finding that we will be having increase in static enthalpy of the fluid medium also. Okay, so as we have H2 greater than H1, so we can clearly say, because here H2 is also greater than H1, and then we are also adding some term Vp square by 2, okay, in order to get the stagnation enthalpy at point 2. So it means that for the case of a moving shock wave, H02 will always be greater than H01. Okay, so it means the process through a moving shock wave is not isenthalpic. Okay, because total or stagnation enthalpy over here is actually changing. Okay, so this is the thing, actually this rise of and total enthalpy is associated with motion of the wave. And if you do recall, in the last to last lecture I have given you one equation, dH naught by dt equal to del P by del T for a compressible flow situation if we neglect the external heat addition and body forces. Okay, so for a compressible flow analysis we can neglect the body forces and external heat addition. So if we neglect these two quantities, then rate of change of total enthalpy will be equal to del P by del T. So as in case of a moving shock wave, we will be having actually variation of pressure with time, so del P by del T will be changing, so we will be having associated change in our total enthalpy also. Okay, so this is one important point. In many times when we do the analysis of stationary shock waves, then we equate over there the stagnation enthalpy on upstream and downstream, but over here we are finding that actually in case of a moving shock wave, our total stagnation enthalpy is not constant and it is actually changing, and its change particularly when we neglect the body forces and the external heat interactions, then its change can be linked directly to rate of pressure change associated with the unsteady motion of the wave. Okay. Now, this is something which we have discussed about the motion of the wave, and if wave is moving, how it is affecting the properties of the stagnant fluid, which is actually getting mass motion. Now, it is important to understand that what is the physical process of wave propagation. Okay, so let's try to understand the. Before that, let's first talk about the situation of a reflected moving wave, reflection of a moving wave. So we have earlier taken the case of sock tube, and in this sock tube we found that when the diaphragm was broken, then we were having a normal shock wave which was moving with w velocity in downward direction, and on the downstream of this, say if my properties are given by 0.1, then in the downstream of this I was having v1 equal to 0, fluid was stagnant, and in the upstream, because this particular wave has now introduced the motion into the fluid medium, so here we were having velocity of the fluid medium as vp. Okay, so this is something which we have discussed. So and we also have come to know that when this wave is passing through the stagnant fluid, then how the properties of the stagnant fluid will change and what velocities these will take. So that is something which we have discussed. Now, important point is that while this wave is actually moving, and when this wave just touches the solid boundary, so when it touches this particular solid boundary, then what will be happening? That is something which is important to understand. Okay, so we know that in case of oblique shock waves, we have studied that if we are having one incident shock wave, when it touches a solid boundary, it will be reflected as a shock wave only. Okay, so by this process, if we see, so what should happen basically, we will be finding that after some time, say our shock wave is at this point, and this is the this shock wave is, say, now reflecting back, moving back, because it has uh, first interacted with the solid boundary, and after its interaction with the solid boundary, it is actually reflecting back in the opposite direction. So when it is reflecting back, say it is moving with reflected velocity wr. Okay, so w was the velocity of the incident wave. Say this incident wave was at some time t1 at this location, and sorry, at time t2 this incident wave has just touched the solid boundary, and then at some time, say t equal to t3, we have the situation then when this reflected wave is actually moving back with wr velocity. Now this is important to understand. When we were having this type of situation, so this situation, this incident wave, while it is passing through the stagnant fluid, it is giving velocity to the stagnant fluid. Okay, so as it has given velocity to the stagnant fluid, so here I will be finding that in this particular portion just before the wave, I will be having actually vp velocity of the fluid. Okay, but what is the situation when this wave has touched the boundary and then after that it is reflecting back? Okay, so what has happened at this reflection boundary? So basically it is important to know that when shock wave is moving, so this shock wave is just going to this boundary, so ultimately whatever the molecules are present at the boundary, it should impart certain velocity to these molecules as well. Okay, because this is the nature of the incident shock wave. But ultimately point is that as this is a solid boundary, so through this solid boundary no fluid medium can penetrate. So whatever the molecules are there, whatever the fluid medium is present in the immediate vicinity of this solid boundary, that should be stationary. Okay, so that is the reason that whenever this particular shock wave, incident shock wave, is actually interacting with this solid boundary, it is reflecting from it, and it is reflecting in such a way so that the fluid which was having velocity vp, it is making it now completely stagnant. Okay, so say if I designate this state as state number 3, which is produced after the reflected wave has passed through this particular fluid medium, then this velocity v3 over here has to be equal to 0. Is this point clear? Why this v3 is equal to 0? The reason is because we have a solid boundary. So the physical nature of the solid boundary is that through which no fluid can penetrate. Okay, so fluid has ultimately come to rest. But when the incident wave has gone, it has imparted certain velocity equal to velocity of mass motion to this fluid medium. Okay, so now from the nature of the problem, what will be happening? We will be finding that a wave will be reflected back from the solid boundary. So this wave will be reflected in such a manner. Now if you see on the upstream of this reflected wave, I will be finding that my fluid is moving in this direction only. Okay, because we have seen that whenever a shock wave moves, then fluid also moves in the direction of the shock wave, but with some velocity vp. Okay, so what we are now saying, that when this wave was moving, some fluid was moving here with velocity vp, and this velocity vp was imparted in this region also. So ultimately the fluid in this region also will try to move through the solid boundary and move in right direction. But because of the nature of this particular solid boundary, ultimately fluid has come to rest. So that's why this shock wave is reflecting in such a fashion so that whatever the fluid was moving with velocity vp, now that sorry, now that particular fluid medium is coming to rest. Okay, so this is the important characteristic of this particular reflected shock wave, that the fluid now ahead of this fluid is having velocity vp, but when this wave will be moving, it will be actually creating once again that fluid as a stagnant fluid medium. Okay, so this is clear. So now in order to understand this process with more clarity, what we can do, we can actually plot in it on some diagram, displacement, position displacement diagram, which is particularly called as the wave diagram. Okay, so say at time t1 this location was x1, at time t2 location of the shock wave was x2, and at time t3 location was x3. So now if I have to plot the xt diagram, say I starts from time t equal to 0, and at time t equal to 0, say my shock wave was at x equal to 0. So this is the point where t is also 0 and x is also 0. So what I am saying is at 0 time my x and t were 0 0. Okay, then shock wave has started, and shock wave has started with velocity w. Okay, and it is moving till the solid boundary at constant velocity of w. So when it is moving with constant velocity w, we will be finding that some location will come in its path which is identical to x1, and corresponding to this x1 location my time is t1. Okay, then further it will keep on moving with constant velocity, but it will keep on moving till it reaches point x2, where my time is actually T2. Okay. Once it has reached at this point, then after this what has happened? Shock wave has actually reflected back. Okay. And it has reflected back with velocity WR. So when it is reflecting back, it means I am once again moving back in the x direction. Okay. But in time direction, I am not moving back. In time direction, I am further propagating in upward direction in next time levels. Okay. So now what will be happening? Now I will be finding that from this point, it has started once again moving back, and at some location, say this is location x3, my time is actually t3. Okay. So this is nothing but this line shows actually this line shows the path of the shock wave, and this path I am also marking with time step as well over here. Okay. And importantly, we will be finding that WR will be less than W. Okay. So when shock wave is actually interacting and reflecting back, its velocity will be less after it is actually reflecting from the interacting and reflecting from the solid boundary. Okay. So now this is the motion of a shock wave. Now say if I want to draw the path of a fluid medium. Okay. So let's consider that I was having some point, some fluid element at this location x1. So this circle is nothing but a fluid element which I am having at point x1. Okay. So whatever the fluid element I am having at location x1, when shock wave is not reached at this point, up to that point this element will be actually stationary. That is the situation. On the downstream of shock wave, what we have? Stagnant fluid, and when shock wave is moving, that is actually imparting motion Vp to the fluid medium. Okay. So what I am saying is that, say if I consider a fluid medium at location x1. Okay. So what will be happening? Up to the time shock wave is not reached at this fluid medium, this fluid medium will remain stationary at location x1 only. Okay. So that is something which I can show, that if this is the fluid medium at this point, this is the fluid medium at this point, then this is at t equal to 0. Now when I increase my time, then also the location of the fluid medium is not actually changing. But when time has become equal to T1, then also fluid medium was at this location only, but now shock wave has passed through this. So when shock wave has passed through this particular fluid medium has been given velocity Vp, and that velocity is moving in rightward direction. Okay. So means after this point, this fluid particle will keep on moving towards the right side. It will keep on moving towards the right side. Then what has happened? Because it is moving behind the wave, so it is moving slow in comparison to the wave. Okay. So this is moving behind the wave, and ultimately at some time it is finding that a reflected wave is actually coming. So this is the location where reflected wave has come. So when reflected wave has come, then once again this particle will be becoming stationary. What reflected wave is doing? So any particle, any fluid medium which is in motion, particularly towards the incident wave, so that fluid medium it is bringing once again to rest position. That is the nature of the reflected wave what we have seen. So ultimately I will be finding that this particle at this point once again will become stationary, and this will remain at this position only with increase of time, unless or until some more incident wave comes and that actually imparts some motion to it. Is this point clear? So this is nothing but the path of a fluid particle. So any fluid particle arbitrarily, if I have taken in a soft tube, so this is how I can plot its path. So initially it was stationary. When incident wave has interacted, then this fluid medium has been given certain velocity, and when reflected wave has come, then once again this particle has become stagnant. Okay, so similar thing you can actually apply for any fluid particle. Okay, so only thing is that its initial location x1 and final location at which it is interacting with the reflected soft wave, that will be different. Is this point clear? Now with this particular second figure, say here I have given state 3 and here my state is actually 2 only, because fluid medium is moving with velocity Vp. So here now if I take the situation, if I fix my reference frame with the shock wave, and then I see, I will be finding that velocity of fluid in medium 3 is equal to WR. Whereas this medium which is coming at from region 2, so this V2 medium will be coming actually with total relative velocity of WR plus Vp. Okay, so now if I fix my observer to the shock wave, so observer will feel that this fluid is actually moving away with some velocity WR, and this fluid is approaching with some velocity WR plus Vp. So for this reflected shock wave, if you see, this particular fluid medium has become incident with velocity WR plus Vp, and medium on the downstream has become actually the downstream medium, which is after behind the shock wave. Okay, so now with this information, if I write the continuity, momentum and energy equations, I will be getting that rho 3 into WR equal to rho 2 into WR plus Vp. Okay. Similarly, I can write down the momentum equation P3 plus rho 3 into WR square equal to P2 plus rho 2 into WR plus Vp whole square. Okay. And then we have energy equation, which will be equal to H1 plus WR square by 2, H2 plus WR plus Vp square by 2. Okay. Now, if you recall, earlier we have written that Ms is equal to, where Ms is nothing but the Mach number of the incident shock wave. Okay, that was W by A1. Similarly, what I can do, I can write down the Mach number of the reflected shock wave. So Mach number of reflected shock wave, Mr, I have to write as WR plus Vp is the relative velocity at which fluid and shock wave are actually approaching. Incident fluid and shock wave are approaching, reflected shock wave are approaching, and properties of the incident fluid medium are designated by state number 2. So that's why A2 I am considering as nothing but the speed of sound for defining the Mach number of the reflected shock wave. Okay, so now if we do once again the similar analysis whatever we have done earlier, using this continuity, momentum, energy equations, and taking the help of these two definitions for defining the Mach numbers, I will be able to find a relationship in between reflected wave Mach number and this particular Mach number. Okay, so from here I will get that Mr by Mr square minus 1 equal to Ms by Ms square minus 1 into square root of 1 plus 2 times gamma minus 1 divided by gamma plus 1 whole square into Ms square minus 1 multiplied with gamma plus 1 by ms square. So this is one important relation. So if you know the Mach number of the incident shock wave, then you can predict the value of the Mach number of the reflected shock wave. Okay, so it means you can know the properties of the reflected wave. Is this point clear? Now let's understand the physical process of wave propagation. So we are saying that some wave is moving, but ultimately what is happening actually? So that is something which is still not very much clear to us. Okay. So if we have to see the physical process of wave propagation, once again we can consider a shock tube, and in this shock tube, say initially I have stagnant fluid, such that its properties are, its density is rho infinity and its velocity is v infinity, which is equal to 0 because it's a stagnant fluid. Okay. Now if I consider a piston cylinder, if I take a piston over here and then if I displace this piston through small amount, okay, so what I have done, I have given very small displacement to this piston. So from say this point to this point. So when I have given this small displacement to the piston, ultimately what I will be finding, I will be finding that the fluid molecules in the immediate vicinity of this piston, these will get slightly compressed. Okay, and because of this compression process there will be some difference of pressure also, and that difference of pressure will try to propagate a wave. Okay, so ultimately we will be able to see that if this is my density versus x, then I can see at some location or at some time t1 my density plot is something like this. So this is rho infinity and this is some higher density over here, and with reference to this I can say as my delta rho. Say this is at some time t1. At some another time t2, at some another time t2, I may find that it has slightly shifted further, and now this is something like this. Okay. So now it is important to understand that when this disturbance has been created, is this disturbance moves by maintaining its shape throughout the entire tube, or does its shape also changes? So that is actually important to understand. Okay, so what we can do, we can have some three-dimensional representation of this wave propagation, and what I can do in this three-dimensional representation, I can consider time axis in this direction. So say this is my time axis, then I can have x in this direction, and I can have a third axis which gives me the difference of rho minus rho infinity. Okay, so on this axis, if I want to say have one wave structure at some time t1, then say my wave structure is something like this. This is at say some time t1. Okay, so here time is say t1. Now at some other time t2, Say my wave structure is something like this. Then at some other time t3, say wave structure is something like this. So now you can see that so this is a wave. Okay, now you can see in all three cases wave is having one tail end. So this is the tail end of the wave. Okay, so what I can do, I can join a line by connecting the tail end of the wave. Similarly, I will be having one head end which is leading. So I can similarly join a line by connecting the, it should come on a same line. So sorry, this is drawn little bit wrongly. So you can consider that your wave is somewhere over here. Head of the wave is somewhere over here. So this is my head of the wave. Okay, and then I can also take a point where I am having maximum density deviation. Say this is the point over here of maximum density deviation. Here in this wave it will be somewhere over here. Here it will be somewhere over here. Okay, now if I join this point also with a straight line, so let me consider here. So I have all these are straight lines. Please consider that I may have done a mistake in drawing it, but all these are nothing but the straight lines. So first straight line is which is marking the location of the tail end. Okay, and what it is showing, that tail is at location x, now at some other location x, at some other location x. So basically it is showing nothing but us, this particular line is showing dt by dx for the tail end. So this I can write as nothing but 1 divided by wt, if wt is my velocity of the tail end. Tail end of the wave. Similarly, this straight line will be my dt by dx for head end, and it will be equal to 1 by wh if wh is the velocity of the head end. Similarly, I can define this as dt by dx of peak, where 1 by wp is actually where wp is velocity of the peak. Okay, so it means that in this process of the wave I am having some velocity wt, wh, wp, and all these velocities can be different, as head velocity, peak velocity and tail velocity can be different, can have different values. It means that these straight lines can converge or can diverge depending upon the values of the velocities. It means that while wave is moving, okay, during the process of wave propagation, it does not maintain its shape. Okay, so shape of the wave can actually change. Is this point clear? So what we are trying to say, that while a wave is propagating, during the physical motion of the wave propagation, its tail, head end and peak can have different velocities. Due to these difference in their velocities, actually we will be finding that our process of wave propagation, during the process of wave propagation, wave does not maintain its shape. Okay, so shape of the wave also change during the process of its propagation. Now, to understand all these concepts and to quantify this, what we have to do, we have to actually understand the wave motion as function of x and t. Okay, to understand wave motion, we have to first derive governing equations for waves, and then we have to start analyzing these equations. Okay, so to do so, what we will do, first we will try to discuss some elements of acoustic waves, because overall behavior of our waves will be nothing but identical to that of the acoustic waves only. Okay, so if I have to analyze any acoustic wave situation, what I can do, I can first ultimately I have to write down the continuity, momentum and energy equations only. Okay, but it is also clear to us, we have seen earlier also, that the process of acoustic wave travel is nothing but an isentropic process. Okay, so let's consider for acoustic waves, our continuity equation, differential form of continuity equation will be del rho by del t plus divergence of rho v vector equal to 0. This is our continuity equation. And then momentum equation is rho dv vector by dt equal to minus gradient of p. And then energy equation I am not writing, but in place of energy equation I will write the entropy equation over here. As the process of acoustic wave propagation is isentropic, that's why ds by dt has to be equal to 0. Okay, so why acoustic wave propagation is isentropic, that we discussed earlier also, while we first time derived the speed of sound. Okay, but here we will take some different perspective to understand the concept of sound wave propagation. Now let's consider that in some wave we have perturbation. So if delta rho is my perturbation in density and say delta v is my perturbation in velocity. Okay, so if these two are the perturbations, then ultimately I can represent my density as rho infinity plus delta rho. Similarly, I can represent my velocity as v infinity plus delta v. Is this point clear? So what I am trying to say over here is that I have some undisturbed flow field. So in case of undisturbed flow field, density was rho infinity and velocity was v infinity, and this v infinity ultimately is nearly equal to 0 if I have a undisturbed flow field. Okay, so it means I have stagnant fluid medium. But now what we have done, say by the process of either by the process of the piston, whatever I have shown you in the previous case, or say right now what I am doing, if I am particularly talking about a sound wave, so I am speaking some words. So when I am speaking something, ultimately I am disturbing the molecules, air molecules which are just ahead of me. Okay, so what I am doing, I am changing their density by amount delta rho. Okay, so that's why rho density has become what was their stagnant density plus delta rho. And then say when I am speaking, if you just keep your hand close, then you will be finding that some flow is also coming. Okay, so it means molecules have got some velocity also. So earlier these were stationary, but now these have got some velocity also. So say delta v is the velocity perturbation which we have actually introduced to our fluid medium. Okay, now with these two, what I want to first study, so we know that the process of sound wave is nothing but a three-dimensional, but let's first consider it for a simplified situation of one-dimensional case. Okay, so if I take this for the one-dimensional case, I have to write all my governing equations in nothing but one-dimensional form. Okay, so in one-dimensional form, I will be getting continuity equation as del rho by del t plus del rho vx by del x. Fine, that is equal to 0, and my momentum equation will become rho del Vx by del T plus what else I will get? Please tell me. Sorry. Del Vx by del T plus rho Vx into del Vx by del X, and that will be equal to minus del P by del X. Okay, this is my momentum equation, and say entropy equation I am just writing like this only, ds by dt equal to 0. So I can expand it in the 1D case as well. Okay, so now my rho is, as I have just now seen, rho is nothing but rho infinity plus delta rho, and V is V infinity plus delta V. So V infinity is 0, so V is equal to delta V. Okay, so now let me make these substitutions over here. So if I make these substitutions, then my continuity equation will become del by del T of rho infinity plus delta rho plus, say here I am using this uh, split differential operator also. So rho times del V by del X. So rho times means rho infinity plus delta rho of del delta V by del X plus delta V times del by del X of rho infinity plus delta rho, and that is equal to 0. Now quantity rho infinity is undisturbed fluid density. So undisturbed fluid density will be a constant value. Okay, so ultimately I can write then this as del by del T of del rho plus rho infinity plus delta rho into del dV by del X plus delta V into del rho by del X equal to 0. Okay, so say this is my equation number 1. Similarly, I can do substitutions in momentum equation. Okay, if I do substitutions in momentum equation, what I will get? Rho infinity plus delta rho into del by del T of del V plus rho infinity plus delta rho into delta V del by del X of delta V equal to minus del P by del X. So say this is my momentum equation. Okay. Now ultimately, though my wave is propagating, but still my fluid medium is nothing but a I can, by taking the help of thermodynamic equilibrium states for a fluid medium, I can write variation of any property, say pressure, as nothing but function of any other two parameters. So say other two parameters I take density and entropy. This is something which I can write for any medium, which is in if I have any simple compressible substance. So from the knowledge of our thermodynamics, I can designate its state by any two independent intensive properties. So that is I have done over here. So P I have written as a function of density and entropy. So from here I can write dP as equal to del P by del rho at constant entropy into d rho plus del P by del S at constant density into ds. Okay. Now, ultimately, because we are talking about the acoustic wave propagation, so the process of acoustic wave is nothing but isentropic process. So, for isentropic wave propagation, ds will be equal to 0. So, ds is equal to 0 for isentropic wave propagation. So, ultimately, I will get that dp equal to del p by del rho at constant entropy into d rho. Now, let me differentiate this equation with x. So, it will become del p by del x equal to del p by del rho at constant entropy into del rho by del x. Now, though earlier we know from our earlier knowledge that del p by del rho at constant entropy is nothing but speed of sound, square of speed of sound. Okay, but at the moment, because we are studying the elements of acoustic theory, so now we will not say that it is speed of sound. Now I will consider that this is nothing but I have some constant quantity a square. Okay, though we know that it is speed of sound, but now at the moment we will be considering it as a constant a square only, and later on we will prove that actually our disturbance what we have, that is moving with this parameter only. So then we will prove that it was nothing but the speed of sound. But at the moment what I have done, I have just said that del p by del rho at constant entropy will be some constant number a square over here. Okay, and that a square into del rho by del x. So if my this is equation number 3, now I can actually make substitution of del p by del x in my momentum equation. Okay, so now if I write equation number 2, then it will be becoming, and rho infinity also, okay, so here it will be, yeah. So what will be happening, rho infinity plus del rho into del dv by del t plus rho infinity plus del rho into del v into del v by del x equal to minus of a square into del rho by del x. Okay, this is the important thing we have obtained. But till now, this constant a square we have obtained, this is for any arbitrary pressure gradient del p by del x. Okay, but ultimately our aim is to represent all the parameters in terms of the known properties. Okay, so other known property can be speed of sound or a naught infinity square. Okay, a naught infinity corresponding to the stagnant fluid medium, because that is something which is a known parameter to us. We know the properties of stagnant fluid, but we don't know what is happening to the properties when wave is propagating. That is something which we want to predict. Okay, that is something which we want to predict. So what I can do, I can relate this a square also with nothing but my a infinity. Okay, so how I can relate, I can say that my A is also a function of density and entropy. Okay, but ultimately entropy is fixed constant parameter for this. So only variation of A will be becoming with density only. Okay, so now using the Taylor series expansion, I can write that A square, if I have to define, okay, by having some gradient of enthalpy. So a square I can write as nothing but equal to a infinity square plus del a square by del rho corresponding to fluid condition infinity, and this multiplied with rho minus rho infinity. So ultimately what happens, when my density of the fluid medium is changing, then my speed of sound is also getting altered. So you have different speed of sound in solids, in liquids, and in gases. So speed of sound, the traveling of sound is an isentropic process. So that's why it should depend on entropy, and ultimately it also depends upon the molecular interactions, because ultimately because of mean molecular collisions only your sound wave actually propagates. Okay, so that is something I have done over here. I have made first dependence of the speed of sound on density and entropy, and then I said that for the travel process of a acoustic wave, our process is nothing but isentropic. So as the process is isentropic for travel of sound wave, so that's why this density is not having any control on that. Okay, so now the control is entropy is not having any control, because entropy is fixed for the situation. Okay, so only variation over here is of density. So how with variation of density our sound can change from the undisturbed fluid medium. So A infinity was speed of sound corresponding to undisturbed density rho infinity. Now my density after the disturbance has been introduced into the fluid medium, density has become rho. So corresponding to this density, my speed of sound has become A. So how I can relate the value of A? By knowing value of A infinity. If I know that my change of density is rho minus rho infinity. Okay, so that is something which I am trying to do over here. So what I have done, I have written the Taylor series expansion. So as per Taylor series expansion, A square, and this I have written for A square, equal to A infinity square plus del A square by del rho infinity into rho minus rho infinity. Okay, so and plus I will be having some higher order terms, and these higher order terms actually I am neglecting over here. Okay, so now from here I can say that A square will be equal to A infinity square plus this rho minus rho infinity will be becoming delta rho times del of A square by del rho when defined at infinity. Fine. So now what I will do, I will make this substitution in equation number 4. So here in equation number 4 I have A square into del rho by del x. So in place of A square I will write this particular formulation. Okay. So if I write this particular formulation in A square, then my equation number 4 becomes rho infinity plus delta rho del v by del t plus rho infinity plus delta rho into delta v into del by del x of delta v, and that is equal to minus A square. So it means minus A infinity square del rho by del x minus delta rho into del square A by del rho at infinity into del rho by del x. So say this is my equation number 5. Okay, so this equation is nothing but coming from the momentum equation, and one equation already I have written which is coming from the continuity equation, that is, let me write it also here, del, please tell me what is the equation, del rho by del t plus rho infinity plus delta rho del by del x of del v plus equal to 0. So this is my equation number 1. So it means that if you are introducing any disturbance, okay, that disturbance in one dimensional case, so in x and time, is given by these two equations. So this is your continuity equation. So here you can see this first term shows with time how your density is varying, and this shows with time how velocity is varying, with space, sorry, and with space how density is varying. And this first term shows how velocity is varying with time, then velocity variation with space. And here we are having linking in between the speed of sound and the density. Fine. So it means that now if I have to find out that how my delta V and delta rho are propagating with space and time, then ultimately I have to find out the solution of these two equations. So these two equations are nothing but the exact equations of our situation. Okay, so these are exact equations of whatever situation we are having in hand. We are having in hand the variation of density and the variation of velocity, and ultimately that variation of density and velocity is also linked to the variation of pressure also, so which we have seen in terms of speed of sound and density variation. Okay, but the difficulty with these two equations is that if you see, these two equations of are these linear or non-linear? These two equations are non-linear. Why non-linear? Because here you can see every term. So delta rho is unknown, del v by del t is unknown. So these are coming in multiplication. Here also number of unknowns are coming in multiplication. Okay, so we have number of unknowns which are actually coming in multiplication over here. So the power of the unknowns is greater than 1. Okay, so that is the reason that these equations are nothing but non-linear. So what we have to do, if we have to simplify further these equations, first we have to linearize these equations. Okay, so first we have to linearize our equations. So in the process of linearization, what we will do, we will consider that our delta rho and delta V are actually small disturbances. These are very small disturbances. So if these disturbances are very small, then if I have anywhere delta rho square or delta V square or product of delta rho into delta V, so that I can make equal to 0. Okay, so ultimately now what we are trying to do, in order to linearize the equations, actually we are considering that we will not be studying the phenomenon for large disturbances. We will be studying the phenomenon for very small disturbances in the flow field. Okay, and because of the presence of small disturbances, these quantities will be 0. So if this is the situation, then let me go to equation number 1. So my equation number 1 will become del rho by del t. Okay, and second quantity of equation 1 will be becoming plus rho infinity into del delta v by del x. Rho infinity is a finite number, that is undisturbed gas density. What about this term? Delta rho will be getting multiplied with del by del x of del v, so that will be negligible, and this also will be small. So from equation 1 I have got this as my, say, equation number 6, and from equation number 5 also if I do the same thing, then I will get rho infinity into del delta v by del t. This I will get, and then this will be 0. here, because I have delta v by x, so everything will be 0. On right hand side, this also will be 0. So ultimately I will get minus a infinity square into del rho by del x. So I can take this to the left hand side and I can write plus a infinity square into del rho by del x equal to, this is my equation number 7. Now if you see equation number 6 and 7, these are the linear equations. These are linear. Another important point is, now these are not exact equations. These are approximate equations. Why these are approximate equations? Because we have taken the approximation that delta rho and delta v are small. So these are now approximate equations, and these will be only exact when my delta rho and delta v are very, very small. Okay, so when delta rho and delta v are very, very small, then obviously these higher order terms will become of very small magnitude, and the whatever the equations we have now got, these will be becoming exact equations for small delta v and small delta rho. Is this point clear? Now let's do one small thing. Let's differentiate equation number 6 with x, sorry, with t. So if I differentiate equation number 6 with t, then what I get? Del by del t of 6. So I will be getting del square delta rho by del t square plus rho infinity into del square delta v by del x del t equal to 0. Say this is equation number 8. Now what I will do? I will differentiate equation number 7 with del x, del by del x. Okay. So if I do so, then I get rho infinity into del square delta v by del x del t plus a infinity square into del square rho by del x square equal to 0. Say this is equation number 9. From 8 and 9, if you see, do you have any common term? From 8 and 9, this term is actually common. Okay, so from 8 and 9 you can say del square delta rho by del t square minus of what is this? This is a classical 1D wave equation. Okay, del square phi by del t square minus a infinity square into del square phi by del x square. So this is nothing but a classical 1D wave equation. Okay, so what we are trying to do from continuity and momentum equation, we have started with the perturbed quantities and ultimately we have reached to nothing but the 1D wave equation. Now solution of this already you have also done, but say what are the key features of this equation and how we can relate the variation of density and velocity with the propagation of the wave, that say I will now take up in the next lecture.